So continuing on with our example of how to apply systematic elimination to solve a coupled system of differential equations. We're working on a system of second order problems that correspond to a coupled mass spring problem. And remember, what we've done is after using Newton's laws to be able to produce these two systems here that describe the displacements of both of the masses, right? We convert those two equations using a differential operator form to this system, right, where d now represents differentiation. So if we have d squared x, that symbolically is equivalent to the second derivative. If we write dx, d concatenated with the x, that's equivalent to a derivative. So we're replacing sort of differential equation components with these variables, all right, with in this case d, so that we can apply linear algebra techniques to solve the system, all right? So what we did is we replaced the original system with using the operator form. And the idea is to eliminate one of these variables, or in this case, the variables are x1 and x2. And what we did to eliminate x2 was find a way that we could get the same terms in front of the x2 in each of those equations. In other words, you'll notice we were able to find a way to get minus 4d squared plus 4, and then plus 4 times d squared plus 4 in front of x2. You do that by applying an operator all the way through, or you can multiply a scalar all the way through. So we multiplied the first equation by d squared plus 4, and the second one just by the scalar 4. And what we do by getting that result is we can add these two equations so that we eliminate x2 altogether. And then we produce a differential operator representation of a differential equation in x1. And what we did is we algebraically determined that this is the same thing as d squared plus 4 times d squared plus 10 minus 16. And what we do is all that is applied to x1 is to write this out as a polynomial form of operators applied to x1. And by doing that, though, we just use algebra to determine that's the equivalent of this form, where we have a product of two quadratics, in other words, d squared plus 12, d squared plus 2, applied to x1. Notice how I'm saying applied to x1. It's multiplied in the equation, but its operator is applied to x1. That can be thought of, though, as just the conversion to two different differential equations applied to x1 that must be equal to 0. d squared plus 12 x1 must be 0, and d squared plus 2 x1 must be 0. So that's the equivalent to these two second order linear differential equations. But then we know what the solutions to those are, just going back to our theory of how to solve homogeneous linear differential equations. We get the auxiliary equations, and we found the roots, which are complex. And what we have is that beta must be 2 on the square root of 3, which is the square root of 12, or beta is equal to the square root of 2. And then, therefore, what we have are two solutions, right, for each of these separate second order problems. So one of the solutions is given by looking at the equations that we had earlier, C1, I'll write this again, C1 times cosine of 2 on the square root of 3, t, plus C2 times sine 2 on the square root of 3t. That corresponds to the solution of this second order problem. But the other problem involves beta just being square root of 2, and this is the solution to that. And so those are two homogeneous solutions that we add together, and we have a total of 4 constants. So what we have is a representation of what the displacement of x1 must be, given in terms of these 4 components. Now, if we want to find it for x2, then we'd have to eliminate x1 from the original equations, or we could use one of the original equations if we wanted to, For example, we could come back up here and say, well, one way to get it might be to apply the second derivative plus 10 to x1 and set that equal to 4x2 and then solve for x2 that way. That's one way to do it. Or we can do the same technique we did earlier. If we go back to the original operator form, right, we have d squared plus 10 times x1 minus 4x2 equals 0. And then we have minus 4x1 plus d squared plus 4 times x2. Again, that was our operator representation of the coupled differential equations, right? So in this time, we're going to eliminate eliminate x1 because we want to solve for x2. So one way we can do that is multiply the second equation by the d squared plus 10 operator. Okay? And then similarly, we'll do what we did before the other one, is we'll multiply the first equation by 4. Okay? So what happens this time? So the first equation becomes 4d squared plus 10, that operator applied to x1, minus 16x2 equals 0. The bottom one, we're multiplying by d squared plus 10 times the minus 4, because you can see, we're getting the same term, just with a negative sign, x1, right? And then we have to be careful. The next one will have d squared plus 10 times d squared plus 4 x2 equals 0. And now we'll add these two. Okay, so we add these two linear equations with the result being that drops out completely. That becomes 0. And we just add all the other terms together and we get d squared plus 10 d squared plus 4 x2 minus 16x2 equals 0. What's interesting is this is exactly the same result we had above, if you look very carefully, for x1. So in fact, we'll end up with the same operator, d4 plus 14 d squared plus 24, all that applied to x2 equals 0. We will get exactly the same solution because they're identical. We're just switching x1, x2. So x2 of t is but different constants. C5, let's say cosine of, we'll write it this way just to make it different. Square root of 2t plus, say, C6 sine of square root of 2t plus C7 cosine 2 on the square root of 3t plus C8 sine 2 on the square root of 3t. So I just wrote it in a little bit different order. But notice these are all different constants than the other one, right? It's a different differential equation. We can't necessarily assume that these constants down here are the same as the constants that we have up here, right? 1 through 4 up there and 5 through 8 down there, right? So we've been able to at least get a form of the solutions. Now the question is how can we figure out what those constants are, right? So in the next video, I'm going to show you how we will use the original differential equations to determine what those 8 different constants are, or at least to eliminate half of them and get all the solutions in terms of maybe 4 parameters. Okay, so what I have here now is we've described both of the displacement functions, x1 and x2, completely, using all the appropriate sine and cosine terms and all of the 8 parameters, right? Notice the x1 and x2 have the same forms, it's just potentially the constants, the multipliers are different. how can we determine what those constants are, or the relationship between them? We're going to substitute these forms into the original equation, one of them at least, of the coupled system. So the one we're going to use to substitute them in is this one. We could use the other one, but we'll do this, the simplest one we can. We'll do this one, right? So what we'll do is we'll literally put in these expansions, these cosine and sine expansions, into this differential equation, right? So what you'll end up having is, say, d squared plus 10 applied to exactly what x1 looks like, all right? So that operator has to be applied to c1 cosine square root of 2t plus c2 sine of square root of 2t plus c3 cosine 2 on the square root of 3t plus c4 sine on 2 on the square root of 3t, right? Again, now we have to put in the x2. So that expansion, that operator would have to be minus 4, right? So we're looking at this differential equation. We're going to take, we've got d squared plus 10 times what x1 is. Now we have to multiply minus 4 times x2. Well, it has this form, c5 cosine square root of 2t. I mean, we're just copying down, same thing, just different constant, c6 sine square root of 2t plus c7 cosine 2 on the square root of 3t plus c8 sine on 2 on the square root of 3t, right? Unfortunately, that all has to be equal to 0. Yay, right? Now it's just a matter of applying these, all right? You're going to have to take the derivative of the first of x1, and then you're going to have to take it and find the second derivative, right? So if we just did that, just so that we can see what the form's going to be like, in other words, if you're going to apply d squared to all of this, right, then the first thing we would have to do is say, all right, so what is the differential operator applied to c1 cosine square root of 2t plus c2 sine of the square root of 2t plus c3, I know it's a lot of writing, cosine 2 on the square root of 3t plus c4 times the sine of 2 on the square root of 3t. What does that differential operator do? Well, we just apply the derivative, right? So we'll have minus square root of 2 c1 sine, taking that derivative, square root of 2t. Now we take the derivative of sine of square root of 2t with the constant there. So that'll be plus square root of 2 c2 cosine square root of 2t. Keep going, all right? Derivative of cosine 2 on the square root of 3t. Well, that's going to give us minus 2 on the square root of 3 c3 sine 2 on the square root of 3t. And then the last one, we're just going to get what? We're just going to get 2 on the square root of 3 times c4 times the cosine of 2 on the square root of 3t. Right? Then, of course, to get the second derivative, right, we'll take the derivative of that term, right? So therefore, if we want to write, well, what will d squared of the original operator, the original expansion be? In other words, we want to know what the derivative of this is. D squared times x1, and here's the original x1. And now I'm going to write all this out again, just so that we can keep things straight. Cosine 2 square root of 3t plus c4 sine of 2 on the square root of 3t. Well, if we want to get that, then we have to apply d to this, right? So let's just do that. So we're going to apply the derivative to that. And then what's going to happen? Well, you're going to get square root of 2 times square root of 2. This will end up being minus 2 c1. It's going to flip back to cosine of square root of 2t. The next term, when you apply the derivative here, right, you're going to get square root of 2 times square root of 2 again, but derivative of cosine is negative sine. So you get minus 2 c2 sine of square root of 2t. And continue on. Now you're going to take the derivative of that term, and then you'll get 12 coming back, right? Because that was another name for the square root of 12. So you're going to get minus 12 c3 cosine 2 on the square root of 3t. And then finally, you'll get another minus 12 C4 sine of 2 on the square root of 3t. Okay? So what we have now is actually a representation of what d squared applied to the original x1 is. And so what we do then is try to simplify all this out, right? In other words, take this form for d squared, then we'll have to have 10 times all of that, and then set it equal to 4 times the expansion of x2. All that simplifies down to the following. I'm going to illustrate, it's a lot of writing here, but it's just pattern matching. And so what we'll end up with, all right, when you apply this first row, d squared plus 10 times the original x1 expansion, and set it equal to 4 times what the x2 expansion is, all right? It'll look something like this. Cosine square root of 2t will end up collecting terms and getting minus 2c1 plus 10 times c1. Where does the 10 come through? Right here, because you're going to end up multiplying 10 times each one of those terms, right? We already have what the second derivative does to it. Continuing on, we'll get plus sine square root of 2t times the quantity minus 2ct plus 10c2. And then we'll have plus cosine 2 on the square root of 3t times the quantity minus 12c3 plus 10c3 plus sine 2 on the square root of 3t times minus 12c4 plus 10c4, right? So all we're doing is we're adding plus 10 for each of those terms there times each one of the corresponding cosines. That's just from the left, exactly what d squared plus 10 is going to do. And that has to be equal to what? Cosine of square root of 2t times 4c5. Right? Because look at what's in front of that term when you put it on the right hand side. Then keep going on. Then we'll have on the left, on the right hand side, sine of 2 on the square root of 2t. What'll be multiplied? 4c6. And then over here we'll have plus cosine 2 on the square root of 3t times 4c7. See, it's just 4 times each one of those. We've pulled it over the right-hand side. And then we'll have plus sine 2 on the square root of 3t times 4c8. And if we have equality, and all of these terms are matching up with sines and cosines, that tells us immediately, right, that, oh, well then you must have equality inside all those brackets and parentheses. In other words, you must have that, for example, combining those terms, you must have that 8c1 must be equal to 4c5, or c5 is simply twice c1. Over here, the next term, we'd have to have this 8c2 has got to be equal to 4c6 for that equality. So c6 must be, again, 2 times c2. Just dividing 8 by 4. Continuing on, right? So negative 12c3, 10c3. We'd have to have minus 2c3 has got to be equal to 4c7. So that means c7 must be negative 1/2 times c3. And then finally, again, we'll have minus 2c4 has got to be equal 4 times c8, which also says that c8 must be negative 1/2 times c4. So what we've done is we figured out that, you know what? There's really only 4 parameters that we have to deal with, simply because to satisfy the differential equation, half of those constants are determined by the other half, the other 4. So we've reduced to 4 parameters overall, because we've described what C5 through C8 must be. So ultimately, here's what we have. we have the original x1 of t, c1 cosine square root of 2t plus c2 sine square root of 2t plus c3 cosine of the square root of, cosine 2 on the square root of 3t. Erase that. 2 on the square root of 3t plus c4 sine 2 on the square root of 3t. Now x2, right? Now we use the relationships we just had. Well, c5 is just 2 times c1 cosine square root of 2t. c6 is nothing but 2 times c2. So we'll have plus to c2 sine square root of 2t. And likewise, we'll have minus 1/2 c3 times the cosine on 2 on the square root of 3t. And we'll have minus 1/2 c4 sine 2 on the square root of 3t. So we have shown that the displacement functions for each of those masses are given by these expansions with sine and cosine, but all we need are 4 parameters. How do we determine those 4 parameters? We use our initial conditions, right? And those had to be given to us, right? For example, we know that x1 at 0 has to be 0, and we also know that x1 prime at 0 has to be equal to 1. We also know that x2 at 0 is also equal to 0, and x2 prime at 0 is negative 1. All right? So how do we use those? Again, we would take these 2 constraints or initial conditions and use them for x1, and we use these 2 for x2 and come up with 2 linear systems. All right? I'll go ahead and show you what they are. When you use the first one, you should get 0. Again, has to be x1 of 0. When you plug in 0 for all the t's in x1, and what should come out is c1 plus c3, right? Because the cosines will be 1 and the sines will be 0. For the derivative term, 1 equals x1 prime of 0. We'd have to compute the derivative of the x1 term, but I'm going to save some time here, all right? What you'd end up getting is the square root of 2, c2, plus 2 on the square root of 3, c4, right? Similarly, for the other one, you'll end up with 0 has to be equal to x2, 0. When you plug in 0 for the x2 expansion, you're going to get 2c1 minus 1/2 c3. And then similarly, if you plug in the derivative, x2 prime at 0, you're supposed to get minus 1. That's going to turn out to be 2 on the square root of 2, c2 minus the square root of 3, c4. Okay? And so what we have to solve is 2 2x2 systems. One of them is c1 plus c2 equals 0, and square root of 2 c2 plus 2 on the square root of 3, c4 is equal to 1, but we want to describe that, right, in terms of 2 equations, right, in the same variables, right? So what we're going to do is, go ahead and write them down. We have those 2, and then we have these 2. 0 equals 2c1 minus 1/2 c3, and then we have minus 1 is equal to 2 on the square root of 2, c2 minus the square root of 3, c4, right? So the trick here is to combine the same terms, right? Combine the equations involving the same unknowns, right? This should have been a 3, sorry. So we combine the first 2 here and say c1 plus c3 equals 0, and 2c1 minus 1/2 c3 equals 0. And we solve those for C1 and C3. And then down here, we'll combine the last two, and we'll have square root of 2 C2 plus 2 on the square root of 3 C4 equals 1. And then also 2 on the square root of 2 C2 minus the square root of 3 C4 equals minus 1. And we'll solve those for C2 and C4. So it's just a little tricky there. We have to make sure we use the equations involving the same unknowns. Turns out, interesting enough, that these two turn out to be 0. Okay. The only way you can get that solved is they both have to be 0. And down here at the bottom, it's not too difficult to show that the C4 term down here is going to be, well, I'll do the first one. The C2 will turn out to be minus the square root of 2 over 10. And then solving for C4, you would get square root of 3 over 5, right? Again, using techniques of linear algebra. So finally, what we have, amazingly, is we actually can write down now what we know the solutions describing the displacements are. Two of the constants are 0 and 2 of them are not. So the final form is the following. We have that x1 of t is nothing but negative 2 on the square root of 10 sine square root of 2 of t plus square root of 3 over 5 sine of 2 on the square root of 3t. x2 of t is negative square root of 2 over 5 sine of square root of 2t minus the square root of 3 over 10 sine of 2 on the square root of 3t. Again, C1 and C3 are both 0. So if you go back to our description of the solutions, x1 and x2, what we notice is that these terms don't exist because C1 is 0 and C3 is 0. So we only have those sine terms. There's no cosine terms at all. So what I have here is a graph. It's very interesting enough to look at what the displacements do. So for example, we just determined that x1 of t is negative 2, square root of 2, over 10 sine of square root of 2t plus the square root of 3 over 5 times sine of 2 on the square root of 3t. And we determine x2 is negative square root of 2 over 5 sine of square root of 2t minus square root of 3 over 10 sine 2 on the square root of 3t. Remember, this describes the motion for mass 1, this describes the motion for mass 2. And you can see they're very different. You can see how the displacement of the top mass is widely varying in the same period of time, that you're not getting as much movement in the second one, right? Illustrates very complicated oscillations, but very different behaviors depending upon which mass you're modeling. Now, for the problem sets, realizing the complexity of how long it took for us to solve this problem because it was a coupled set of second-order equations, we're just going to do coupled first-order equations in the problem set and on any exam question, whether in the online portion or in class.